Welcome to the first lesson of multivariable calculus. We will be starting off with dot products. We will be starting off with dot products, and then we'll be moving on to other vector stuff. But for now, we're gonna start off with dot product. What is the dot product? The dot product is also known as a scalar product. A scalar product, because what it does, it gives a number with one property, and that is magnitude. Um, there's a lot of vocabulary surrounding this. Magnitude is how much something has, basically. Um, so the scalar product gives a magnitude, it gives a number, it gives an amount, it gives a quantity, right? It doesn't give anything else. It just gives a quantity that could be used to describe something else, but it doesn't give anything in particular. So there's two ways to denote these vectors. The first way, the dot products, first of all, the dot product is concerned with vectors, right? Vectors are something that has direction and magnitude. So, for example, a vector like this and a vector like this may look like they have the same magnitude, but they point completely different from each other. So when you add them, they will not give a vector that's double the magnitude. They will give a vector that's maybe not even half the magnitude. So that's why vectors are important, because they have a direction as well. It could be completely opposite, or it could be anywhere within the space that you have. But anyways, we're not going to get too deep into that. A dot B, there's two ways to denote vectors. One is bold, like this, and the other one is, okay, I forgot to bold this, but one is bold, and the other one is with the arrow on top, like that. So there you go. So this is how you calculate dot product. Simple. If A is 2, 3, 4, and B is negative 1, 6, 0, I'll give you guys time to calculate it, and I will calculate it right now. So 2 times negative 1 plus 3 times 6, and that is the answer. You could include 4 times 0, but it's not necessary, because 0 is just 0. Anything times 0 is 0. 2 times negative 1 plus 3 times 6, 16. 3a times 2b. So if you have a number before a vector like that, that means distribute the 3 to each component of the vector. So 3a will be what? 3a will be 6, 9, 12. And 2b will be what? 2b will be negative 2, 12. So that is 6 times negative 2, negative 12, plus 9 times 12, 108, 96. 96. Oh, I'm sorry. This still needs 3 components. It's not a 2D vector, so it still needs 3 components. Don't make the same mistake. If it has 3 components like this, you cannot dot product to a vector that's in 2-dimensional space, a vector that only has 2 components, and a vector that has 3 components. You can't do that. Next is A dot A times B dot B. Now notice I don't put a dot in here, and there's a reason why. So to calculate that reason why, for me to tell you what that reason is, I first have to calculate this. So A dot A is 234.234. That's simply each of them squared, and then you add them together. So 4 plus 9 plus 16 is 29, times B, each of them squared, add them together, 37. Now you could put a dot in here, but it's just another symbol wasted. There's no reason to put a dot in there when you can just have multiplication of 2 numbers. As I told you, it's a scalar product, so you get a number out of it, you don't get a vector out of it. And because you get a number out of it, you don't have to put the dot in there, because multiplying 1.2 will be another way to multiply vectors that will give you a vector. So but numbers, when you multiply them, there's only one way to multiply numbers. So that's why we have this this method. This is 1103, I think. 37 is 1110. No, it's not. It's not 1103. It's 1110 minus 37, which is 1073. There you go. Next, these are the properties of dot products. A dot A gives you A squared. So basically, that's what I have been. That's what I told you for this calculation to make it easier. Just square all of the components. What is this symbol right here? The symbol with the absolute value over it. Sometimes you'll see it like this instead, with two absolute values over it. It means magnitude. It means the amount that the vector has, right? The power of the vector, or the substance of a vector. Right? These two vectors have equal magnitude, but they have different direction. So when you calculate the absolute value, or the it's called the modulus. If you calculate the modulus of the vector, you will get the distance of the vector, and you could just use the Pythagorean theorem or the distance formula to calculate that. That's pretty easy. A dot A is A squared. A dot B plus C is a distributive property. Or I should probably put arrow vector. So A dot B plus C is A dot B plus A dot C. A dot B is equal to B dot A. PEMDAS still applies, by the way. CA, or I'm sorry, C is a scalar. CA dot B is equal to CA dot B is equal to A dot CB. And the 0 dot A equals 0, or the 0 vector dot A also equals 0. So prove property 2. Let's prove property 2. Let's do it. So if we have a I'm just going to say three dimensions. So we have A is equal to A1, A2, A3, and then B is equal to B1, B2, B3, etc. Right? And C is equal to C1, C2, C3. Then B plus C is B1 plus C1, B2 plus C2, B2 plus C2, B3 plus C3. And if you do A dot this B plus C, you will get A1 times B1 plus C1 A2 times B2 plus C2, and then A3 times B3 plus C3. And then if you do it this way, you will have A1 B1 plus A2 B2 plus A3 B3 plus A1 B1 plus A1 C1 plus A1 C2 plus or A2 C2 plus A3 C3, and you will get the exact same. I don't have enough space to fit this. I would, if I would do it, but I didn't think that the proof was going to take this long. So that is it, I guess. A dot B, yeah, this is the formula, the geometric formula for your interpretation, for your A dot B equals AB cosine theta. So this is your geometric formula for the dot product. This will only give you the magnitude. So in fact, I should probably do, or actually, it doesn't matter because A dot B gives you the magnitude anyways. So this will give you the magnitude. This is definitely correct. And if the two are not perpendicular to each other, or then cosine theta can be interpreted as A dot B over the absolute value of A, the absolute value of B, like that. So yeah, it's just moving A and B to the other side around. Yeah, this is a geometric interpretation basically. So the angle between the two vectors and the two vectors that you have And so the dot products will be like this. What is a projection? First of all, what's a projection? A projection is it's what you call when you have some part of something onto something. For example, if you want to project this vector onto this vector, then you take this. If you want to project this vector right here onto this vector, then there's this much of it to project, because this vector is moving kind of up and to the right, but it's not moving. It's like not all of its component is on the vector. Not all of its component is coincides with the vector. When you move it down a little bit, when you squish it down a little bit, it's not. You're not going to get all of the magnitude to fit onto this vector right here. So you only get this much. You're not going to get all of this. So if this is, I don't know, 4 long and this is 6 long, maybe you're only going to get 3 out of the 4 to project down. You're not going to get all 4. So that's the projection. That's what a projection is. This is a scalar projection, so it will tell you how much of this vector is on this vector. Yeah, and the vector, the unit vector is, this is the unit vector. It usually indicates direction. So if you want a vector projection, if you don't want a scalar projection, you already have how much, the magnitude of what you need, which is this, that's the magnitude, and then you have this unit vector right here, which is the direction. It has magnitude 1, but there's a vector to point out the direction. Yeah, so you multiply them both together. You multiply the scalar projection gives the magnitude, and then you multiply the unit vector, and that gives you the magnitude and the direction for a projection of A onto B. So a picture would be like this. That is the projection of A onto B. Or, I'm sorry, the projection of B onto A. But it's written like this. It's a little bit weird. That's B and that's A. This is a projection of B onto A, but it's written as projection sub A of B. Projection sub A of B. But it's probably not said like that. It's said as projection of B onto A. So that's how it works. Okay, next exercise is find the angle that this vector makes with the x, y, and z axes. So well, first of all, I don't know if you can even picture the x, y, and z axes. That's x, and usually that's y, so usually that'll be z. It goes something like this. Use the right hand rule. It's a right-handed coordinate system, so use the right hand rule to determine your axes, or you could always put I probably actually put the x right here, the y right here, and the z right here. Right, it still works using the right hand. Actually no, it doesn't. I'm sorry. What if I put the yeah, this is a mess. If I put the x right here, the y right here, and the z right here, it should work. Okay, so x how much? 1. Y how much? 2. So it's something like this, and then 1, 2, 3, 4, 5, like right here. Something like that. What we want is to find the angle that this makes with the x-axis, find the angle that it makes with the y-axis, and then find the angle that it makes with the z-axis. It's a little bit tough, but let's the actual way to find it is simply just, it's something called a direction cosine. So the cosine of the angle, the cosine of whatever angle you're trying to look for, I'm just going to use theta, is equal to the component. So for example, the x component, right? I'm just going to write the entire word out, component over magnitude. That's the cosine, right? I'm not gonna try to calculate it out on the phone, but you guys can do that by yourself. So basically, A is equal to, well, if you want to find the directions that each of them make, for the x-axis we have cosine theta x equals 1 over square root of 30, which is the magnitude. 1 squared plus 2 squared plus 5 squared is 30. Square root of that is 1 over square root of 30. It is distance. It's distance formula. Theta y is 2 over root 30. And theta z is 5 over root 30. Same thing for here. Cosine of theta x is minus 2 over root, this time it's 2 squared plus 3 squared plus negative 1/2 squared is 13 and 1/4. Cosine of theta y is 3 over square root of 13 and 1/4. And cosine of theta z is negative 1/2 over square root of 13 and 1/4. And that's how you calculate your direction angles, direction cosines. Okay, let's do some problems. So find the scalar and vector projections of B and A. So this is a scalar projection, this is a vector projection. And remember, you take A dot B over root A. So A dot B over root A. First of all, I need to explain to you what I, J, and K means. I is a unit vector on the I direction, on the X direction. J is a unit vector on the Y direction, and K is the unit vector on the Z direction. So put it simply, it basically just means A is equal to 2, negative 1, and 4, and B is equal to 0, 1, and 1/2. That's simply it. So the projection of B onto A, like that, is equal to A dot B, which is 1 over the absolute value of A, which is, or this is component. This is what this is actually a component. So I would actually write comp, and then the projection is the same thing, but it's a vector product instead. So projection of A onto B is 1 over times, so 2 times negative 1 times 4, or 2 squared plus negative 1 squared plus 4 squared is, I think it's 21. 21, so root 21. So this is 1 over root 21 times A over A. So I think it's 2 over root 21, negative 1 over root 21, 4 over root 21. There you go. Number 44. Same thing. These two are actually orthogonal, I think. So let's find out if they are. So A is 1, 1, 1. B is 1, negative 1, 1. So the component of A onto B, or the component of B onto A, I'm sorry, is equal to dot product with each other. So that will get you 1, and then over root 3. So 1 over root 3. And then the projection of A of B onto A is 1 over root 3 times 1, 1, 1, and they're all over root 3. Right? Yeah, if you square all of them, you should get the correct, yeah, you should get the correct projection. This is the projection right here. Now show that the vector of orthogonal, orthogonal means perpendicular, so show that the vector orthogonal of B, the orthogonal of B onto A is equal to B minus the projection of B onto A. So this is the projection of B onto A. This is B, this is A. So if you take minus the projection of B onto A, what is minus projection of B onto A? Minus is the other way around. So you'll get this. So this is projection of B onto A, negative, minus projection of B onto A, like that. I'm sorry about the loud noise. But if you just do this, then you will get this. This is what you'll get. So this is projection of B onto A, but the negative, right? So then if you add B and the negative projection of B onto A, or if you subtract projection of B onto A from B, then you will get this right here, which is the vector completely orthogonal, right, to A. So these two are perpendicular to each other. They're completely perpendicular to each other. So when you dot product them, you'll get 0. And this is just the opposite of what you want, right? This is the opposite. This is the component of B that is orthogonal, that is perpendicular to A, rather than onto A. So that's how you would prove it geometrically. If you want to prove it algebraically, put in the comments. I'll pin your comment if you are able to do it. Find an angle between a diagonal of a cube and one of its edges. Let's try. So if you have a cube like this, or let me draw the 3D system first. Right? Let me draw the 3D system, and I can be assured to you that this is x, this is y, and this is z. And then you have a cube. If you have a cube, let's draw the cube. So it will look something like this. And we want one of its edges and the diagonal. So what's the diagonal? The diagonal is 1 in every direction, 1, 1, 1. So let's do A is a 1, 1, 1. And one of its edges can be anything. So let's do B is 1, 0, 0. Right? It has to be 1, 0, 0 or 0, 1, 0 or 1, 0, 1. It can be any of that, right? But all of its edges move only 1 in one direction. So 1, 0, 0 and 1, 1, 1. So then we have our cosine of theta is equal to A dot B over root A dot B is 1 over absolute value of A, absolute value of B, root 3. So theta is cosine inverse of 1 over root 3. Now, same thing with 56, diagonal of a cube and diagonal of one of its faces. Wherever you go for the face of the cube, the diagonal of a cube will always go only, or diagonal of one of its faces will only go on 2 directions. So let's say we have B new C. Let's say we have a vector C is 1, 1, 0. So it will only go on 2 directions, 1 and 1. That's how you do a diagonal of one of the faces. It could be 1, 0, 1. It could be 0, 1, 1. But it can only be, or it could even be negative, I think. But it could only be one of its faces like that. It could only happen like that. So A dot C is 2. And then over the square root of 3, square root of 2, root 6. So cosine of, let's say, phi. So this would be, I don't know, this would be theta, right? And then if I drew another, I'm sorry for the cursing. If I drew like this, then this would be phi. This would be phi, something like that. So cosine of phi is 2 over root 6. So phi is cosine inverse of 2 over root 6. And that's it. I hope I didn't do it wrong. That's it for today's episode of the first ever lesson in multivariable calculus. I hope you enjoy it. I will do more episodes later on. We're gonna get into very, very exciting territory later on. This isn't really that exciting yet. I don't know about me. I don't know about you, but this isn't really exciting for me. I would like to teach more on the double and triple integrals, but we're going to get to them later. For now, that is going to be it, and I'll see you next time.